So today we're going to start off with the concept that's going to be the most central, important thing that will carry throughout the entire course, and that is the concept of electric field. So electric field is, of course, has to do with the electric interaction, and the electric interaction affects objects that have a property called electric charge. So let's just talk about electric charge first. Electric charge is a property of matter, right? Much the same way that particles have mass, and anything with mass is affected by the gravitational interaction. Certain particles have charge, electric charge, and they are affected by the electric interaction. So charge is measured in units that we, in the SI system, are called coulombs, and the abbreviation is just capital C. And there are lots of different particles that have charge, right? So name some particles that have an electric charge, some familiar ones. Electrons. Okay, electrons have charge, right? In fact, let's give the mass and the charge. So the mass of an electron is about 9.1 times 10 to the minus 31 kilograms. But its charge, anybody know what the charge of an electron is in coulombs? Is it positive or negative? It's negative. Okay, so it's negative 1.6 times 10 to the minus 19 coulombs. Okay, so right away we see a difference from mass. Mass is always positive. Charge can be positive or negative or zero, right? What else? What other things have charge that we know? Protons have charge, right? So a proton has a mass. It's a lot heavier than an electron. Protons have a mass of 1.7 times 10 to the minus 26. Minus 27 kilograms. So it's small, but it's about 1,000 times more than heavier than an electron. But the charge is positive, same thing, right? Positive 1.6 times 10 to the minus 19 coulombs. And this size of a charge comes up so often that we actually give it a special name, little e, which is a little unfortunate because little e is used for so much, but we'll often use it to indicate the charge of a proton. So little e is a constant equal to positive 1.6 times 10 to the minus 19 coulombs. So this is the proton charge. What else do you find in an atom? Neutrons, which have a mass close to, a little bit heavier than that of a proton, but close to 1.7 times 10 to the minus 27 kilograms. But the charge is neutral, which means the value is 0. Okay, so it has no electric charge. Okay, and so these are the three things that are most familiar to us, right? Because protons and neutrons make up nuclei, and electrons surround the nuclei in an atom. But there are all sorts of other charges, or particles with charge, I should say. Anybody ever hear of a particle called a positron? What is a positron? Yes. It's a positive electron. It's the antiparticle of an electron, right? So it turns out in nature that for every type of particle, there is an antiparticle or antimatter, which has the same mass, 9.1 times 10 to the minus 31 kilograms, but the opposite charge. It's actually a positively charged electron, 1.6 times 10 to the minus 19. And so we can also have an antiproton, right? An antiproton would have the same mass as a proton, but the charge would be, what would it be? Same as an electron's, right? Negative 1.6 times 10 to the minus 19 coulombs. And on and on. There's there's a whole host of more exotic types of particles like kaons and muons and various other things, pions, that have electric charges. And we may talk about some of them as we go along, but just to give you sort of a sampling. So charge is, we say charge is quantized. Meaning it only comes in units of this positive or negative proton charge. Okay, you can have zero charge or 1 electron or proton charge or twice as much of an electron or proton charge or 3 times, etc. But there are no intermediate values, with one exception. It turns out that there are particles that make up protons and neutrons that are composed of constituent particles which are called what? Anybody know? Quarks. Yeah, these are made of quarks. And quarks can actually have charges of 1/3 e plus or minus 1/3 e or plus or minus 2/3 e, but the caveat is that no one's been able to find a quark isolated from other quarks that make up protons or neutrons or other types of particles. They can only bind together in such a way as they make particles with a single value of E, okay, an integral value of E, and isolated quarks, as far as we know, just can't happen. Okay, so there are exceptions, but we can't really observe them in nature. We have to sort of infer their existence. Okay, so that's charge. And what do we know about charge? When we bring two positive charges near each other, what do? They repel. Okay, so I bring a positive and a positive near each other. They're going to exert repulsive forces on each other, right? And if I bring two negatives near each other, what do? They push apart also, right? They repel also. Okay, so these are, I'm drawing force arrows here, force vectors. So like sign charges repel, but if I bring a positive and a negative nearby, what do? They attract. Okay. So we have an attractive force. So can we quantify this? The magnitude of this force depends on what? Okay, depends on distance. How does it depend on the distance? Okay, so there's a constant here. You said kq1, q2 over r squared. So I'll just call this some constant. We'll talk about what this constant is. It depends on the charge, right? So if these things have some amount of charge, we'll call it q1 and q2. Then that will influence the force. The bigger the charge, the bigger the force. And it's dependent on 1 over the distance. 1 over the distance squared, right? 1 over the distance squared. So if this distance is r, okay, then if I have two particles near each other at some distance r, and if they're now at a distance that's twice as far away, if this is now 2r, what happens to the force? It's 4 times smaller, right? It goes down by a factor of 4. Divide by 1 over 2r squared, you get 1/4 r squared. So this is now 1/4 of the force we had before, okay? So for a lot of you, this is review. A lot of you have seen this before. This might be new to some of you. And we'll deal with this more as we go along. Now, so we know how the electric force behaves and how these charges exert forces on each other.